Hey everybody, my name is Dan Friedman and I'm a data center solutions engineer at Cisco. I support national and regional partners with our data center product portfolio. As of late, that portfolio is expanding to include infrastructure in support of artificial intelligence. As a result, I've spent a decent amount of time over the last few months learning fundamental AI concepts. For those of you that are trying to do the same, I've tried to capture what I've learned into this introduction to AI presentation. Lots of specific terminology which may be new to you will be introduced, and hopefully I'm able to do this in a way that helps you make sense of the chaos. So before we get into the agenda and the slides, I want to pose a sort of problem statement. And the statement is this: humans have capacity limitations. We have all probably encountered individuals who behave as if they know it all. I know I have. But the reality is, humans cannot possibly know everything about everything. The breadth and depth of knowledge that's available to us is simply more than we can realistically consume, store, or remember. As a result, we pick fields of study that we can focus on. But even within our chosen field, the knowledge available to us is still quite vast. The knowledge is also nuanced or specific in that sometimes the knowledge only applies in certain circumstances. So again, the reality is we can't really know everything even within our own chosen field. And when we don't know something about our own field of study or some other field of study, we need some help. We need a tool to help us get the information or knowledge that we need. Back in grade school, we used to use the Dewey Decimal System and a card catalog to help us find books containing the information that we needed. Starting in the mid 90s, as the internet was built and more information became available online, we started using search engines to find the information we needed. Today, we're starting to use artificial intelligence more and more, but its capabilities now stretch beyond just knowledge acquisition. So, what is it, artificial intelligence? Well, according to the movies, AI is a computer that can behave like a human. The computer's ability to receive information, process it, and respond has a human like quality to it. Artificial intelligence is essentially the process of attempting to embed human knowledge into a computer so that we humans can turn around and use the computer to help ourselves solve problems. So, if using artificial intelligence to help humans solve problems is the goal, how exactly do we accomplish that? How do we teach computers what they need to know to most effectively help humans? I'll do my best to explain what I've learned so far in a coherent way, but understand this is a complex topic that I'm still trying to master myself, so I'll have to jump around a little bit. From an agenda perspective, we'll introduce a bunch of terminology, products, and talk about the history and progression of AI and related technologies, the requirements for success with AI data and different approaches to training, generative AI and related discussion points, model customization methodologies, and then the AI app development process and associated software suite. There's only about 8 slides covering all this content, so we're going to spend a decent amount of time on each slide describing the bullet points in detail. At the end, I present an additional slide that talks about recent Cisco product announcements that will help customers in this space. Finally, I don't consider myself an AI expert. I'm still learning just like most people, but I am attempting to tie together information gathered from many sources and to paint a general picture and explanation of concepts. So please take this with a grain of salt and continue to use additional sources of information to educate yourselves. All right, let's go ahead and get into the meat of things. So let's start with a high-level description of the progression of AI technology, which I think provides a decent backdrop and a context for the rest of the presentation. Artificial intelligence itself has been around for quite a long time. Initially, it was used mostly from a pattern matching or detection perspective. The most common example of this is fraud detection. In the case of fraud detection, we try to understand and describe the normal spending behaviors of a credit card holder. Normal spending behaviors might be characterized by which cities the credit card holder spends money in, at which stores, and in what relative amounts. A sudden deviation in these spending habits could indicate a stolen credit card and/or fraudulent transaction attempt. Pattern matching or detection, at least conceptually, is simple and straightforward. but there are other use cases that we are interested in solving for, such as classification, segmentation, prediction, and even recommendation. So, taking things one step further, we have machine learning. Machine learning is a set of complex and elegant mathematical techniques used with data to try to make a prediction. Using data to make a prediction should produce more accurate results than a random guess. That's why machine learning is also referred to as data science, i.e., using a scientific approach to prediction. If we boil away some of the mathematical complexity, basically this has to do with plotting and then interpreting data. If you think about it, you can collect, plot, and interpret data about just about anything. Maybe you want to try to show how your child's health is impacted by the amount of sleep they get. This isn't exactly a pattern matching problem, it's more complex and varied than that. You probably have some predictions about this relationship already with zero data or math involved, and you might be right. But collecting and analyzing data will help tell a clearer story, which might confirm what you already believe, or it might surprise you and challenge your beliefs in ways that you didn't anticipate. Maybe you think that less sleep means poorer health, but the data shows otherwise, and maybe that's because too much sleep means not enough time for other important things that help impact health in a positive way. In this way, data can provide insights that you may or may not have even been looking for. Companies the world over have lots of data about their own businesses and want to be able to leverage that data to gain insights into their own business, to enable their own employees, and to inform better business decisions. Now, taking things another step further, we have deep learning. Deep learning is the act of building a model to understand the probability that one piece of data is related to another. Under the hood, a deep learning model is implemented as a neural network. A typical image of a neural network is shown on the slide with inputs on the left, outputs on the right, and hidden layers in between. To keep it high level, when you hear the term AI model, think of a deep learning neural network, which is essentially a mathematical lasagna. Yeah, that's right. A lasagna, just like a lasagna, an AI model is made up of many layers. But instead of noodles, meat, cheese, and tomato sauce, we're talking about layers of linear algebra equations. Each equation represents the likelihood that one piece of data is related to another. This, at a super high level, is how artificial intelligence works. The idea is that you can feed loads and loads of data into this AI model, and much like the human brain, it will learn. AI models are very good at performing a specific task that they were trained to accomplish. Going back to some of the use cases, things like detection, classification, segmentation, etc. Once the model has been trained, it can make decisions without consulting outside sources of information. Human learning requires one or more feedback mechanisms which are there to help improve performance over time. Similarly, AI models include feedback mechanisms to improve performance over time. Fast forward to today, we now have generative AI. Generative AI, as its name suggests, generates something. This can be text, images, video, or music. Generative AI can tackle several different types of tasks related to language, including summarization, translation, coding, image generation, and even biological sciences discoveries. Generative AI is the topic of discussion for the rest of this presentation, as this is what is garnering so much market attention today. But before we get into the details, we still need to lay a bit more groundwork. So let's talk a little bit about the requirements of generative AI. So what's required for AI to be successful? Well, computers consist of hardware and software, so we're going to need both of those. Hardware is what does the computational work under the hood. It's the engine which powers the vehicle. Software gives us access to the capabilities of the engine. It's the application and or tooling built around the engine which makes the engine useful. Skills are what we need to know to leverage the hardware and software towards our goal, which in this case is artificial intelligence. We need knowledge about the hardware, the software, about deep learning, and about application development. As we've already learned, machine learning provides the functional underpinnings of what makes artificial intelligence work, and developers help tie everything together by enabling users to make inquiries to a system or an interface and receive results which reflect the predictions made by the AI ML engine under the hood. The skills are a given, so now we're going to focus on hardware and language requirements of Gen AI. Then a bit later, we'll talk about the software stack and the included tools. All right, so let's talk a little bit about the hardware for processing requests. CPUs process data serially, one question at a time. Item 2 can only be looked at after item 1 has been dealt with. This is a relatively slow process. GPUs, on the other hand, process data in parallel, multiple questions at one time. This means items 1 and 2 can be dealt with at the same time. Obviously, this is a relatively quicker process. GPUs are also more energy efficient than CPUs. To be clear, GPUs require more power in total than CPUs, but the amount of power required per GPU core is less than what's required per CPU core. Speaking of cores, GPUs pack thousands of cores, each acting like a little calculator. Each calculator works in parallel to slice through all the mathematical equations that make up an AI model. In addition to the parallel processing offered by a single GPU, we will eventually have a need to scale our system up and out. To do that, we'll leverage NVLink and NVSwitch technologies. NVLink is a high-speed connection for GPUs and CPUs that lets these processors send and receive data from shared pools of memory at lightning speed. Today, NVLink connects hosts and GPUs at rates of up to 900 gigabytes per second, which is about 5 times faster than current PCIe technology. NVLink on all 8 GPUs in an NVIDIA DGX system share fast direct connections via NVSwitch chips. Together, they enable an NVLink network where every GPU in the server is part of a single system. In other words, any GPU can talk to any GPU very quickly, allowing them to operate more as a single large GPU than as individual units. NVIDIA is the most well-known company advancing GPU technologies today. NVIDIA offers both hardware and the software needed to take advantage of GPU technology. Chip designers like Intel, AMD, and NVIDIA all have different architectures. Each chip architecture represents some new leap forward in technology in terms of processing power and features or capabilities. Cisco UCS server families like M4, M5, M6, M7, and most recently M8 closely follow the architectures of the underlying chip makers. Cisco supports at most 2 architectures at once, the current architecture and the previous architecture. Today, that means once we fully announce all M8 servers, we'll continue to support the M8 along with the M7, which is the predecessor, but we will end of life the M6, and anything prior to the M6 is already end of life as of today. NVIDIA's current GPU chip architecture is known as Hopper, and the next architecture is known as Blackwell. The H100 and H200 are the most ordered GPUs on the market today, but NVIDIA continues to expand the capabilities of their chips. In the future, we'll have Blackwell, B100, B200, etc., and these will get built into Cisco's products. Now, in the context of AI, different amounts of processing power are needed for different tasks. There are essentially 3 things that we can do with a model. 1, we can build the model. This is known as training. 2, we can customize the model. This is known as fine-tuning or RAG. And 3, we can consume the model. This is known as inferencing. We'll define training, fine-tuning, RAG, and inferencing soon, but for now, just understand that on a spectrum of potential processing power, building the model requires the most processing power, or GPUs. Consuming the model requires the least processing power, or GPUs, but still needs to scale to meet the number of consumers and requests coming from those consumers. And Customizing the model requires an amount of processing power or GPUs that typically falls somewhere between building and consuming. All right, so next let's talk a little bit about language. Every language has some fundamental constructs like nouns, verbs, and adjectives. There are other constructs, but these are the main ones that everybody remembers. Nouns represent people, places, and things. Verbs represent actions done to or with the people, places, and things. And adjectives represent attributes or descriptions of the people, places, and things. If you take a step back from these details, what you'll realize is everything that we as a human race know, whether real or imagined or conceptual, can be expressed or encoded via language in a variety of formats, including text, speech, images, videos, music, computer code, etc. Now, let's understand a little bit about how models learn. Supervised learning is when the data that you use to train your model is labeled. You can think of this sort of like a database where each column represents some attribute of an object. If you have a database table called customer, you may have columns like name, address, phone number, birth date, etc. Those column names are the labels. So training a model requires massive amounts of data, and a common challenge for enterprise customers is that they simply don't have enough data to train their models with. Labeled data, to be precise. Having a labeled data set makes it easier for the model to learn. Imagine training your model on thousands of images of cats and dogs. If each image is labeled, it makes the job of training the model that much easier. This is the idea behind supervised learning, but creating a massive labeled dataset can be time consuming or even error prone. So, unsupervised learning is when the data that you use to train your model is not labeled. This naturally presents more work for the model to attempt to learn whatever it can learn. It is given no labels as hints about what it is supposed to learn. As a result, this type of learning is used when a company might be seeking to learn something from its data that it doesn't already know. What new patterns or discoveries might be made? This will likely require more compute resources than labeled training and may require a larger model. Few-shot learning is when you train your model and you give it some examples. For example, this is a cat. But zero-shot learning is when you train your model and you give it no examples. You just let the model figure things out for itself. These are some terminologies that you might hear when talking about AI training. Okay, so up until this point, we've talked about how deep learning or AI models can be trained to be very good at a specific task, and how everything that we know can be expressed and is encoded via language in one or multiple formats. So imagine if we could train a model using trillions of words. Then not only would the model be able to understand our request in multiple formats and be able to respond to our request in multiple output formats, but it would also have an opportunity to acquire the knowledge about everything that the language itself is describing. All the nouns, verbs, and adjectives, all the relationships between them, all the knowledge and nuance that language conveys about everything ever written about on the internet. Basically, the model can learn about everything humans have ever documented or theorized about online. Such a model is called a large language model. Large is part of the name because of the large amounts of data that the model is trained on. Language is part of the name because the model is trained using various formats of language or communication. LLMs include something called parameters, which are essentially a measure of the strength and or capacity of the model. A model with 250 billion parameters can learn significantly more than a model with 25 million parameters. A model with 250 billion parameters will also require more hardware resources to run efficiently. As an example, the largest llama model currently includes 405 billion parameters. Not all models are generalists, though. You can build a model to suit any more specific need. For example, Bloomberg GPT is a model built for the finance industry which contains about 50 billion parameters. This is still a large model to be sure, but it's more specialized in its knowledge than Llama and requires fewer resources to run. An LLM is trained on huge amounts of text, language, code, images, video, music, etc. As a result of its knowledge acquisition about language itself, as well as all of the things that language can describe, a LLM is well suited to solving a broad spectrum of problems across many industries. Using its learned knowledge, it can make predictions. The predictions aren't always correct, though, and these are known as hallucinations. Remember, AI is based in data science, using data to make predictions. Predictions can be facts, but are not always facts. Also, when models are trained on data, there is the potential for models to learn bias. Other challenges with LLMs include data privacy, intellectual property ownership, and specificity. We said before that in the context of AI, there are three main things that you can do. One, you can build a model. This is the training that we've been talking about so far. Two, you can customize the model. The reason that we'd want to customize a model is to give it more specificity. Basically, to convert the model from being a generalist in terms of its knowledge into a specialist in terms of its knowledge. And then finally, three, we can consume the model, which we'll get to a little bit later. Now seems an appropriate time to introduce the concept of a foundational model. Given all the data and compute resources needed to train a model like Bloomberg GPT, maybe you're a finance company, and rather than train your own model from scratch, maybe you'd like to leverage and benefit from the training work already done by another entity. A foundational model is a pre-trained model that can be customized to address your company's specific needs. I tend to think that the larger a foundational model is, the stronger it is, the more capacity it has to provide predictions across a vast array of topics. The smaller a foundational model is, the weaker it is. The lesser capacity it has to provide predictions across a vast array of topics. Both models will still know language, but may not have been exposed to as much language, reducing its learning and therefore knowledge capacity. So, where do you get these foundational models? Well, there's a website called Hugging Face, which basically serves as a repository of foundational models. You can download a model and use it as is, or you can customize it. The more customization that is necessary, the more skills and infrastructure you're going to need, so the higher the cost. Let's say, for example, that you downloaded a model which understood the English language, but it learned nothing other than the language itself. If you ask it a question, it won't know the answer. It might respond, "Hey, I don't know anything other than the English language. Ask me questions about grammar and punctuation." Now let's say you wanted to use this model at your company so that you could ask it questions about your company's products. Except the model doesn't have any knowledge about your company's products. It only knows the English language. This is where customization comes into play. So, what types of customization are there? First, we'll talk about RAG because it's easier to understand. RAG stands for Retrieval Augmented Generation. With RAG, you give your model access to an external source of data outside the model itself. You can think of this like a folder on your hard drive. Inside that folder, you save documents which contain detailed descriptions of all your products your company offers. Now, when you ask the model a question, it interprets your request in English, then it hands off the request to another model which maintains an index of all the content in your folder. It tries to match the request to one of the items in the index. Then it goes and looks up the detailed information in the document based on the index pointer, and that detailed information is returned to your model and then to the user. Basically, RAG is a way of attaching additional external information to the model in addition to what the model already knows. This is one way where we can convert the generalist model, which knows English, into a specialist, which also knows your company's products. Companies everywhere are starting to use RAG to enable their internal employees with more timely and accurate information of all kinds. Second, we'll talk about fine tuning. Now that you understand RAG, the easiest way to explain fine tuning is this. Fine tuning is taking some external knowledge and baking it into the knowledge of the model itself. The knowledge is no longer located in an external source like with RAG. The knowledge is now part of the model. This is another way where we can convert the generalist model into a specialist which knows to focus its responses on a certain topic. Fine-tuning requires more upfront resources to accomplish, but can result in lower latency responses and doesn't have to consult an external repository of information. All right, so we've talked about building the model, which is training, and customizing the model, which is fine-tuning or RAG. Now let's talk about consuming the model. How do we enable users to consume the model? This is where our AI ML developers and the software stack come in. But if you think about it in simple terms, AI is just another type of workload. Businesses have been running applications for a long time. Every time you deploy a new application, what questions do you have to answer first? What are the application requirements? What resources does it need to run? How much CPU? How much RAM? How much storage space? How much network bandwidth? What kind of throughput, requests per second, and latency response times are we looking for? What kind of availability do we need in terms of redundancy and data backup or restore capabilities? What kind of scalability do we need? Scaling up, scaling out, or both? What kind of data persistence do we need? We still need to answer all these same questions with an AI-based workload. But with AI, we also need to add some additional questions to the list. What kind of GPU resources are needed to run this workload? Do we need more than one GPU? If we need more than one GPU, will they all fit in a single server, or do we need multiple servers? Which GPU should we select that's best for our particular use case? What underlying network infrastructure will be needed to support an AI application which is distributed across multiple servers? The answer to these extra questions is topic of debate in the industry right now. Many customers know they will need AI to be competitive, but don't know how to answer what are my AI application requirements. They haven't built their applications yet, and the lack of experience prevents them from stating or predicting what resources they will need. As a result of this and lengthy lead times for GPU hardware, many customers are going out and buying up more resources than they need. They are guessing, which can lead to low utilization of GPU resources, i.e., a waste of money in the short term. In the long term, once they get some AI application experience under their belts, they will probably wind up using those resources by adding additional AI projects. Okay, so from a hardware perspective, we need extra GPU, and it may need to be distributed across multiple systems. Got it. Now what? Now let's try to bring it home by talking a bit about the AI application development process and how this is related to the underlying software stack. There are many components to the software stack, and I think they're best understood in the context of the application development process. What does development of an AI application look like? What are the steps? So first, we said that we're going to require a lot of data. So step one is all about the data. Data collection, analytics, preparation, and loading. Data collection is, the data needs to source from somewhere. So what are your sources of data? What formats is the data in? And is it in a format that your model can consume? Data analytics, what insights can we gain from the data in its native format? Data preparation is about cleaning up, reformatting, and labeling your data if appropriate to facilitate model learning. And data loading is about loading all of the curated data into memory where it'll be accessible at speed to the model as the model goes through its training exercises. The most common tool for data preparation and loading is Apache Spark. NVIDIA Rapids for Apache Spark is the GPU-enabled version of Apache Spark, meaning we can accelerate the work Apache Spark does with our data. Now that we have the data, we can use it to train the model. NVIDIA Tau, PyTorch, and TensorFlow are examples of frameworks. There are others that are used to move the training data set through the model to train the model. Now that the model is trained, we need to test the model using a new data set that the model has never seen before. This helps us validate that the model learned what we intended it to learn and that it can now be used to make accurate predictions based on a sample of real-world data. NVIDIA TensorRT can be used for this. Finally, once the model passes testing, we can deploy the model into production so that corporate users can consume it. NVIDIA Triton Inference Server can be used for this purpose. We talked about build, customize, and consuming a model. Consuming a model means using it. Inferencing is another term which basically means consuming or using the model. At this stage, the model has been trained and is available to be used on a server like any other business application. You can make requests to it, i.e., ask it questions, and it'll provide predictive outputs as a response. There are many product names here on the slide, and we've really only just scratched the surface. NVIDIA AI Enterprise, otherwise known as NVAIE, is the collection of software mentioned above, plus more. The idea is to leverage this pre-packaged suite of software to manage your AI application development pipeline. The other idea is that GPU acceleration and features are made available to developers through each stage via these software components. Customers, of course, have the option of using open source tools and community support in building their own software stack, but this requires a lot of skill and experience. And let's face it, community support often leaves a lot to be desired. Customers buy NVAIE because they're looking for an enterprise-grade experience, especially in terms of security and support. With it, they will receive technical support for software, frameworks, libraries, and workflows, and all of this results in speed to value. NVAIE comes in two licensing tiers. Essential covers everything in red on this slide. As named, this covers the essentials, basically everything needed to manage all of the stages of AI app development. Riva is a premium license if you're going to be doing speech AI, for example, in a call center type of application. There's a couple of other acronyms or vocabulary items that you're likely to hear about. CUDA is a programming language for developers. CUDNN is a library that developers can use for deep learning. NeMo is a software framework for building, customizing, and running your own LLMs. And workflows are intended to streamline the development process. Since I'm not an application developer, I'm not too sure how these fit in with NVAIE or the other products that we've already discussed. At this time, I need to do more studies and research to figure out how these items fit into the big picture. All right, that was a ton of information and it's gone by pretty quickly. I hope that I presented it in a way that was digestible and felt like a coherent end-to-end story. We started with the basics and tried to introduce a lot of vocabulary along the way. We ended up with the complexity of the app development process and software stack. Arguably, the GPU and hardware piece of this conversation is relatively simple and easy to understand. Certain GPUs fit certain use cases better than others, so understand your GPU models and what they do best. The software stack is arguably more difficult to understand due mostly to there being so many product names. The more you can understand the AI app development process and tie products to those stages, the easier it will be to remember them all. The complexity certainly lies here, and as with DevOps, you can build your own stack or go with a more curated solution. So, with that said, let's try to wrap this up. Cisco understands many of the complexities and challenges of AI. To that end, we're trying to simplify things for our customers. Today, we can provide the compute and network infrastructure needed to run AI workloads. AI Pods simplifies ordering by leveraging a single SKU backed by a CVD to provide a full stack validated solution. AI Pods come in different sizes depending on the model size and use case. AI Pods range in capabilities which allow them to support smaller inferencing deployments, medium sized RAG or fine tuned model deployments, or full size training needs. Most customers are going to be adopting generative AI. Most customers will begin with one or two AI projects, ramping their knowledge, their skills, their experience, and ideally their success over time. With experience and success will come the demand for multiple AI projects, which will require the AI environment to scale. AI Pods is a modular architecture which will enable customers to scale with ease. Next up, we've got Hyperfabric. Hyperfabric is Cisco's newest cloud-managed AI-ready network fabric. It has the speeds and feeds to support compute-intensive workloads like AI. Cisco manages the hardware, the operating system, and the switch configuration provisioning. The customer manages the overlay or data plane, what traffic it wants to transport over the fabric. The primary use case is as a solution for customers who don't need the customization offered by either NXOS or ACI fabrics, but they want an easy button solution that is quick to deploy, easy to manage, and ready for AI-based workloads. Next up, the compute portfolio. There are more announcements pending within the Cisco compute portfolio. Stay tuned for more information, but the idea is that Cisco will absolutely provide a complete and compelling compute portfolio that is AI ready. Cisco also wants to help customers purchase what they need. To that end, a lot of cooperative work is happening right now between Cisco, Intel, AMD, and NVIDIA so that we can provide accurate sizing information based on the model size, hardware resources, and use cases that your customers wish to run. Finally, today you can purchase NVAIE through Cisco or build your own stack. Cisco recommends NVAIE. Building your own software stack is not recommended unless you have deep AI ML skills and expertise to secure and support your toolset solo. Generative AI to me is all about solving problems which range from general problems to specific problems. I hope that this presentation was helpful in your understanding of basic artificial intelligence concepts. Thank you for watching.